Glad to have you here. We have two presentations for you during this session. The first one is a team that has repeatedly impressed me throughout the semester. This is a team that took on what was easily the most difficult project of all the senior design projects, and I admitted at the time that I was not optimistic, and the outcome has really impressed me, and I hope it impresses you as much as it did me.
Hello everyone, this is Team Stoplight. Our senior design project is a window celebration. Our whole team lead is Nicole, and principal lead is Kyle, and team members John and myself, Nor. Our faculty advisor is Albright, our industry advisor is Miller, and our client is Dr. Kennedy. First of all, I'm going to go over the functionality of the device, how it is built and designed. The device, also, we're going to talk about both electrical and mechanical aspect of the device. Then we're going to move into the calculation. We have both actual and theoretical. Then we're going to show you some challenges we had and a demonstration at the end. So what is a wind belt? A wind belt is a device that harvests a wind energy and converts the wind into electricity so that it can power different electronic devices. For our case, it's a cell phone.
Okay, so to start off talking about the mechanical aspect of our project here, we have two stands on the side that are detachable to allow for portability. As you can see, both of them come off, and in the middle here on the frame we have a hinge and a simple gate and clasp hook, and this can just be popped off and folded in half and transported with the stands. The frame here, the gray part, is made out of PVC pipe. That's to allow for inexpensive materials and as well as durability for the outdoor conditions. The Spectrolite tape we used here for the membrane, the blue part, is it's basically a hobby item used for fish lures, but we chose it because it's durable, like we said, for the outdoor wind speeds, and also to allow flexibility for the oscillation. The coil mounts here, what we use to hold the coils into the frame, are made from plexiglass and plastic screws, and this is to allow for easy holding of the coils, and at the same time not to interfere with the electromagnetic field of the coil or the magnets, as you can see down here, and as well as not to allow for any power loss that we might get from the circuit. The whole concept of our device mechanically operates off of something called the aerodynamic flutter effect, and you mostly hear about this when bridges collapse, but on a non-catastrophic level it can be used to produce energy.
So the major power generation components of the device are these two black things right here. These are coils, 1,000 turn coils a piece, hand done. It took a lot of time. That then leads to our ADC converter, which stands for analog to digital converter. So when you're moving magnets within coils themselves, they create AC current, which kind of goes like this. With this component right here, the 4 diodes in a certain configuration, that changes that AC current to a completely positive current. Then the big element right here, the capacitor, then smooths out the signal to where it turns into more of a DC signal. Next slide, please. So here are the major equations that you're going to need to use to sort of calculate what's going to happen. First, the magnetic flux, that's the basic magnet itself. Due to the magnetic field strength from the magnet, as well as the physical dimensions of the magnet, basic surface area A, and as well as the angle in which it interacts with the coils, allows for the phi value, which is how much voltage you're going to be able to create. So when I said 1,000 turn coils, that's the N value in that equation, as well as the flux value, and then that's with respect to how much frequency of the magnets interacting with the coils, with the membrane flapping. So whenever you're dealing with a project like this, the main questions are voltage, current, and power. What we calculated for voltage is about 5 volts, which is correct for a cell phone battery, about 10.256 milliamps of current. That allows for about 10 hours to a full charge of a cell phone battery if you're using a 1,000 milliamp hour cell phone battery. Most cell phones use that, which then leads to a 51.543 milliwatt power. Go ahead. So as you can see, what we calculated wasn't what we actually got out of the device, we got a lot less than we predicted. And as you can see, it kind of escalates. So if you don't have the proper voltage or the proper current, then your power is going to be shrank dramatically. And that goes along with some of the issues that we found in the project.
All right, as you're probably thinking by now, we have had a lot of challenges with this project. The first, as mentioned, there is non-ideal construction. This is due to the fact that our entire team is electrical engineers. The biggest problem we have had with this device is its physical construction. We needed to talk to ME students, ME professors, the shop techs, just to understand the variables, the notation, the definitions, many different things to actually build it to the way it was supposed to be. The next issue or challenge was the inner workings of the cell phone battery. This is because this is a company's actual product. They do not want anyone to know what's inside it because then you can steal it and make it yourself. Because of this, we had to test days after days of voltage, current, and resistance to try to guess what was inside and then try to make a chart from that. Due to the complexity of that, we eventually switched out the cell phone with the LED that you can see, and this is to demonstrate a proof of concept and show that it is still possible to generate voltage with wind. The last challenge we had was a misunderstanding of equipment. This is because we knew how the devices and equipment works separately in the lab, but when we strung them together to test, we eventually found out that we were short-circuiting part of our circuit, which is why we did not get what we needed. The curve, the curve rectified waveform, that is what Kyle was talking about when he said what the analog to digital converter does. The red line is what the capacitor does, and that's what we want, so that would be easier to charge the device.
So here we're going to go through a demonstration. So, as you can see, here's our power source, wind. Here's the device. Turn it on. You can see it start flapping. The membrane is oscillating the magnets within the coils. And we have a little switch to make sure that we can charge without it being on. And there's our LED. So we were actually able to get something working. We were able to get some electricity out of just wind, but we weren't able to get it to the proper level. As you can see, it's not a constant light on the LED. It's kind of flickering because the current's not constant. But if we had a few more months, we possibly could get to a cell phone.
Although we were not able to charge the cell phone, we were able to light an LED, so we have a proof of concept. And I hope you guys enjoyed our simple presentation, and we'll be happy to answer some questions.
Any questions? Yes.
Who came up with this idea?
Do you mean to do this, or the actual invention of a wind belt?
Both.
The actual invention of a wind belt was made and designed by a person named Sean Wayne.
Sean Fain in 2008. It was in Popular Mechanics. He patented the design. He has a company called Humdinger, and he produces these on a regular basis. I kind of saw a YouTube video of this, and I thought, whoa, renewable energy, this would be so fun and easy. It's not as easy as we think.
Any other questions? Yes. Yes.
What potentially do you see that being applied towards? What size experience?
Well, you can parallelize this just like if you were going to paralyze solar panels, except it utilizes just a different type of energy. You can put an entire wall of a house, or just make a wall of these guys so wind just passes through it. It's more efficient than actual turbine because it requires more wind to turn on a turbine. This requires little wind to actually activate. So in that respect, if you had some sort of a spring breeze throughout your house and you just wanted to make a wall of these guys, you can charge a little bit. You can charge maybe your lighting system or something, but it has potential to grow.
Why did you choose to have your device horizontal instead of vertical?
That is because it was As you can see, we have not a normal fan. One of the challenges we had was circulating wind stream. When we tried to use original fans, big circular fans, it created like a cyclone effect, and that was hitting unevenly throughout the membrane, which eventually switched to this straight fan. And to answer your question, it's easier to find a horizontal fan than a vertical fan.
Another thing to add is that the oscillation wave you want is they call it a single oscillation, where it does that moving, and if you like take a snapshot of it, it looks like an oval. Whereas I think if you would have it this way, you wouldn't get the same. You kind of want the multiple oscillation wave, and like John said, I don't think we could invert fans that way.
How much wind, I mean, once you get this thing so it really is working, how much wind would you need? I mean, obviously if there's no wind, it's not going to charge your cell phone. If there's a 2-mile-an-hour wind, do you need a 20-mile-an-hour wind? What kind of wind speeds are we expecting in order to be able to make this useful for a cell phone?
So we were, like we said, we did multiple testing with fans, and we had as low as 5-mile-an-hour winds, and that it wasn't moving. It kind of did this little wiggle thing, but it wasn't moving at all. And then we went to 10-mile-an-hour winds, but that was with the circular fan, like a regular floor fan that you'd see. And I'm not sure if it was because of like we said, it wasn't a laminar airflow, but that wasn't giving us the results we needed. And the lowest this fan could go to is 24 miles an hour in the second setting. And somewhere between there and 15 miles an hour was the lowest we could get, but we basically didn't have enough fans to test as low as we could go. So right now, as far as we know with our device, it's 24 miles an hour winds. And that's a little unrealistic. For example, in Honduras, where Dr. Tandy would be going for summer to maybe test our device, their maximum average wind speed is 15 miles an hour. So it's a little unrealistic practically, but that's as far as, like I said, as far as we know, it's 24 miles an hour. It could be lower. We just don't have the fans to test it with.
I can tell that you guys were a little bit disappointed because you didn't get to charge the phone, but I just want to say that this is a great proof of concept, and seeing that LED light up, I don't know about everyone else, but I was excited. So good job. I'm just curious, you mentioned you have a customer, Dr. Kennedy, and that you guys may actually want to deploy this later on in, was it Honduras?
Yes.
So do you have plans to continue working on this?
Well, honestly, the last time we talked to him about that was in fall, when the portability aspect of our concept was, our project was a requirement that he introduced for that, and so he did talk about taking it down there for summer, but I'm not sure that we haven't talked about it since, basically.
Okay, thank you very much, guys.